chapter 8. We're going to go ahead and talk about number 1. I went ahead and thought about this for you. I wanted to kind of put this in a better picture for you, so I took a little bit of time and I made this. I hope it helps. So we're going to talk about neutron bombardment. Let's go ahead and read the question out loud. Radiocarbon dating of artifacts depends on the slow and constant production of radioactive carbon-14 in the upper atmosphere by neutron bombardment of nitrogen-14 atoms. The neutrons come from the bombardment of other atoms by cosmic rays. Write the balanced nuclear reaction for the process that converts N14 to C14. So there's our skeleton equation, our N14 to C14. I just want to go ahead and talk about this really quick before we go further. I want to talk about these numbers here. That's N14, C14. This N14 here, this is an element by itself. This is what we had to start with. So it's going to have 7 neutrons, 7 protons. We know it has 7 protons from the periodic table. Okay? And then we said it went to C14. They gave us the mass number. They gave us a total amount of protons and neutrons, but they gave us 6 protons here. So we know this can't be 7-to-7 ratio, okay? And we'll get into that in 1 second. I want to show you the picture. We'll talk about that. It'll be a lot easier. So let's talk about neutron bombardment. So remember we said bombardment's like dodgeball. We're gonna throw these neutrons at somebody. We're gonna throw these neutrons at somebody. This is a proton with a P in the red. This is a neutron with an N. I went ahead and put 7 P's in here, and I went ahead and put 7 N's in here. This is my nitrogen atom, okay? My nitrogen atom is right here. And we're gonna do neutron bombardment, okay? And these neutrons are flying in the air, in the atmosphere, cosmic rays, fine. One's gonna strike the nitrogen atom. When it strikes the nitrogen atom, a proton, let's say this guy right here, this guy gets knocked out of the club, all right? He gets knocked out. He gets pushed out. If we hit this with a neutron, a proton comes out. And that's what we said here. We have 7 protons here, and we have 6 protons here. We knocked a proton out. So let's go ahead and let's represent that over here. We're going to say we have a proton over here. Now, if we're going to say we took this neutron and we hit it, we're going to have this neutron stick in here, like that. It replaced that proton, okay? So this is what our picture looks like now. We had a neutron bombardment, we hit this nitrogen atom, a proton left, that neutron stayed with the molecule, okay? So let's go ahead and put down what we just did in the formula. So we had a proton eject this proton right here. We're just going to write up here plus P. It's a 1 proton. I have 1 proton, 0 neutrons, 0 neutrons. So my number here should be a 1. Let's go back over here. We had to use a neutron to cause all this. Let's put this neutron right here. Let's put this neutron right there. A neutron has no protons. It has 1 neutron, okay? So this is why the math looks right in here, okay? Let's talk about this guy right now. I want you to see what happened here. How many protons do we have in this ball right here? 1, 2, 3, 4, 5, 6. We know that has 6 protons. 6 protons. How do I equal 14? What happened here? How many neutrons do I have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Eight plus 6 is 14. I have 1 more neutron because I added it. I have 1 less proton because I ejected it. I'm going to put that there. I'm going to put this here. My math is correct. I really hope this picture helps.